Today we'll be talking about automatic defect classification for the semiconductor industry for outgoing quality inspection. So title is a bit of a mouthful, but we'll explain as we go through. We have Ander Anelturk here, as well as myself, Quinn Killow. With that said, I want to jump in and just talk about our agenda really quickly. So we'll do a quick intro of ourselves and our companies and their backgrounds. And then I'm going to hand it over to Ander, who's going to talk a little bit about the semiconductor process and the challenges around it. Also the kind of previous approach and limitations to the process that we were looking to automate here with computer vision. And then I'll take over and talk a little bit about Data-Centric AI and how exactly that relates to our product, Landing AI's product called Landing Lens. How it was applied to this project in particular, and then I'll turn it back over to Ander to discuss key results, and then time permitting, we can jump into questions and answers. So with that said, maybe we can do our quick introductions. Ander, maybe you can go first.
My name is Ander Anelturk. I'm a senior member of the technical staff in NXP. I've been with NXP, Motorola, Semiconductor, and also Freescale for about 23 years, basically working in yield enhancement group and dealing with all the defectivity stuff that we have.
Great. Thanks, Ander. And I'm Quinn Killow. I'm with the business development team here at Landing. I've been with the company for 4 years now, mostly working with the users of our product to help deploy these computer vision solutions to automate various visual inspection tasks. My background is in the manufacturing space. I've spent my whole career working on automating different tasks. In the last half of my career has been really focused on computer vision and machine vision. So it's a really exciting topic for me. With that said, I will turn it back over to Ander just to give a quick introduction on who NXP is and what they do.
For NXP, Semiconductor probably it's one of the biggest manufacturer of the semiconductor chips that are actually going into our automotive industry and most of our daily uses, and be it in our phones or TVs, anywhere that we actually have a chip that we are making for our daily use. And the total quality, of course, vision that we have in NXP is the most upfront, mentality we have, the foundation of our working theme, and the idea there is that we want to first time develop the right thing and design and qualify it with a zero defect to our customers and provide flawless customer support. As I mentioned, the quality mindset is a big culture in our company because it's being used in our daily lives. Just to get to a better, safer, and smarter, secure world. NXP is there.
Great. Awesome. Thanks, Ander. And just to give a quick background on Landing, so we're a company that provides software to make computer vision very easy. We aim to kind of lower the barrier to entry, so you don't have to be an expert to come in and build impactful solutions. Our main product, our flagship product, is Landing Lens. It's 100% of what we're focused on, and really it's a tool that users can come into and build, deploy, and manage these computer vision solutions for a really wide range of applications. The product itself, we aim to make it really easy to use, make it so that people can come in and build accurate results fast, and also able to deploy those solutions easily. So we have a bunch of flexible deployment options because it's great if you can build a model, but ultimately you need a way to actually leverage that model, right? And we also focus a lot on scalability. So working with clients such as NXP, deploying one solution isn't always the end goal. They want to kind of deploy a number of solutions, and that's really what we're aiming to deliver with Landing Lens. And then just a quick note on the types of applications that we're focusing on, or types of industries that we're focusing on. Today, we're talking about the semiconductor space, but we do have a pretty wide range or breadth of industries that we talk to and work with success across all of them. So semiconductor all the way to automotive, or even doing aerial imagery from satellites. A lot of what we do is in the manufacturing space, but certainly not what we're limited to. So that's kind of a background on landing AI. Now I think we can kind of jump into the meat of it and start talking about the application specifically for NXP and what Anders is working on. So with that, I'll turn it over to you, Anders.
If you go to the next, please. Yeah. So just to give a brief explanation of how a chip is being made, starting from a silicon wafer at the very bottom, we build different types of transistors, and as the wafer goes along the process flow all the way to the end of the fab or factory, we actually build the transistor. As you can see, there may be two types of transistors, PMOS and NMOS, and we actually have, they are just the different types of transistors. And from the poly, from the active region to poly and contact, as you see, as you go up the line, you actually build up metal lines, interconnect lines to access to those devices in the chip to make the functionality of the die or the chip that we process. And as you see, the complexity of the process is very apparent here. That this process takes about 2 to 3 months at minimum from the silicon wafer all the way to the end of the line. And throughout the whole process flow, of course, to check the quality of the processes and what we have built up to that point, we do certain inspections. And I notated here as to what we call front-end inspections and middle-end of the inspections, and types of the defects that we observe in these inspections. Of course, as you go along the process flow, you would see all these defects, and you would accordingly control your processes for what these defects are generated for. But at the very end of the process, what we are actually going to talk about here is the automated outgoing inspections that we do. Even if we have controlled all the defectivity and process throughout the whole flow, we actually get to the end of it, and we still make another quality check because of that mindset of the quality for the die to be either rejected or not rejected. And you can see on the colorful images, the optical images, the reference versus a defective die, you would actually reject this die. And even if you didn't detect the defect up until that point, this will be the last point before the chip is being sent to the other sites to get packaged and electrically tested. So before this point, there is no electrical test, but after this point, the chip is being sent to a package, and then electrically test, and then either rejected or not rejected. So the application that we have up at this point are for this automated outgoing inspections, where we inspect and hopefully detect all the defects that we have on the dies and reject them accordingly. And this is applicable for all the dies that we produce in the fab. That's why the data volume gets a lot extensive. That we need to make the classification of these defects as automated as possible, but reliable in that regard, so that we can actually either reject or send it to packaging. Next, please. So the problem that we have is of course, if you look at any vehicle, for example, for the automotive industry, this is a data that we gathered from the Gartner And as you see, as the years go by, the number of chips that we have in an automotive in a car goes more than 600 and even more in the coming years. However, our expectation from our customers is to get less defect per million, so that the quality is actually is getting more and more stringent, and this requirement actually makes you want to do the inspections and do it reliably and reject accordingly, so that you have less defect for less defective parts per million to be sent to our customers. Next, please. Yeah. So as I mentioned, with this quality mindset in our minds, as we are actually inspecting all the parts of all the technologies of our chips, as I mentioned, the data volume gets immense per day. You know, we may actually get up to 20,000 images to be collected from the inspection tools at the outgoing inspections, and every one of them is being classified. Up until now, we were actually using the human classification, and human classification is involving one user, or I would say operator, technician, sustainer, or engineer, looking at the defective images or whatever captured and classify that as if whether it is a reject part or not. So because of this manual intervention, you are actually dedicating a lot of resources from at the workflow to classify these. However, from the training of these operators and experience of these classifiers actually may vary, and that may actually introduce some errors in our classification. However, we wanted to include this automatic defect classification so that we can actually reduce the time for classification and the quality of the results that we get from day-to-day classification. And just to allude a little bit of the classification, as you see, we do the processes at this point. This is an outgoing inspection. The process is done. The inspection is the next step, and after the inspection, we usually do the classification by looking at every single image. And as I mentioned, it may reach up to thousands of 10,000s of images per day to be classified. Next, please. To look at this classification, previously we, of course, if you're not using the manual classification and you want to use an automated version of it, you usually look at a confusion matrix. What we call the confusion matrix is you basically tabulate what is predicted versus what is a true classification in terms of the ground truth, and you try to align true positives and true negatives as if the ADC is classifying in human classification. And there are two parameters that we have been using in this classification. It's either a recall or a precision. Precision is how accurate the ADC classifies the defects, and the recall is how accurate the classification is distributed to the predicted classification. And at the end, what we are trying to get is to try to maximize both of them so that we can actually rely on the automatic defect classification. And the same is applicable for a given multi-class automatic classification. And here also you are trying to maximize both the precision and recall. And our approach is a little different, and that's why we were successful in implementing this in our manufacturing.
Great. So now I wanted to hop back over and talk a little bit about how landing lens plays into this ADC process, and also about this kind of concept of data-centric AI. So I want to take a step back really quickly. I know we jumped into the technical piece of this a little bit, but just computer vision 101, just to level set the playing field here. I'm sure a lot of us are aware already, but just to highlight, computers are really interpreting and analyzing data such as images or videos when we're talking about computer vision, and we're leveraging artificial intelligence to do that. It should be noted that there are a lot of different types of computer vision, so different types of models that do different things that are better at certain tasks. But in general, they're all looking at either an image or a video, and they're finding areas of interest or doing classifications or classifying the entire image. So with these tools together, the technology as a whole is pretty broadly applicable. You can tackle really wide range of use cases using these tools. And I think it's worth mentioning some of the advantages of computer vision. So like why even look at this in the first place? I think a lot of this ties back to this project in particular. So first of all, consistency and speed. By automating a task with artificial intelligence, you're able to get much more consistent results from a model. If you show the same image multiple times, you'll get the same results. Versus a human, they might change their inspection based on their mood for any given day, right? Scalability is another piece of this, right? With a computer vision solution, you can easily scale it out to multiple locations, multiple applications. It's a more standardized implementation when you compare it to some of the more traditional technologies. So I'll talk a little bit more about the development process in the coming slides, but essentially you follow the same basic steps for creating each computer vision model. So it allows you to kind of do that scalability that we're talking about. And dealing with variability. And this is a really big point for computer vision. It handles changes in images very well, right? It can deal with variability across different products or across different applications, whereas something that's hard-coded might have a little bit harder of a time doing that. And it's really with these benefits in mind, and with the advent of new tools such as Landing Lens, that we're really able to kind of lower the barrier to entry for these computer vision applications and allow folks like NXP or other companies to start broadly adopting the technology. I think it's worth mentioning some of the breadth of the application of computer vision. So we're talking about the semiconductor space here, but it can be applied in a number of industries, like I mentioned earlier. So I have two example use cases here on this slide, just to give kind of an idea of where it can be applied. So first of all, we have a steel inspection process. This was a manufacturer of steel rolls. There was a hot rolled steel application. They had a really fast moving conveyor with the steel on it, and they had an array of cameras looking at that steel, and they needed to find defects and do classification on them. It was a process that was done manually in the past, and they were able to automate it with computer vision to make it much more reliable. And then all the way on a totally different industry, on the right-hand side here, these are pharmaceutical images for pharmaceutical discovery. So this was a process where scientists had to look through microscopic images and basically segment out different cells that they're seeing within those microscopic images. It was a really tedious process, and the resources to do it were really expensive, and they were able to automate that with a segmentation task built in Landing Lens. So kind of highlights the breadth of what we can do with these computer vision products. And I think it'd be helpful to walk through kind of the simple workflow of Landing Lens. So like, what are the basic steps? So first of all, you upload data. So you have maybe an image data set or video data set, and you would upload that to our product. Once you have that in the product, you would have a data set to work with, and you can start using our user interface to label images. So in the case of an object detection model, you'd be drawing bounding boxes over the things that you want the model to find. Once you've done that and you've kind of cultivated your data sets, you go into the train phase, where you essentially take that data set and have the model learn the task that you're trying to automate. And we make that really simple with a single button click. And then the last piece is really the prediction, right? So how do you actually leverage that model that you've trained on now production images, right? So we have, like I mentioned earlier, a bunch of flexible ways to deploy these models into production and start leveraging them. And I think it's really important to notice or to note the importance of data in these applications. The field of AI has largely been founded around really massive data sets, really these public data sets that have hundreds of thousands or millions of images. And that helps when you have those really large data sets to kind of wash out some of the noise. So if you have mislabeled images, you can wash it out with thousands of good ones, right? But when you go into these more niche applications in the manufacturing or fabrication space, a lot of times the data sets that we're working with aren't as massive, and you can't count on the volume to outweigh the noise in the data. So the quality of the labels that you're producing is super important. And I really like to use this use case here to kind of exemplify that. This is also a steel application. And these are some of the different defect categories that a customer was looking for. So rolled in scale, patches, grazing, et cetera. It looks pretty straightforward when you look at them side by side, but when you start looking at unlabeled images, you might be able to, this one's probably pretty easy. That's probably a patch, right? Pretty straightforward. This one as well, you might quickly categorize that into the scratches category. But then you look at this last image, it could very easily either be the rolled in scale or the grazing defect category here. And someone doing the labeling might throw it into one or the other, and it might be correct or incorrect. And having an incorrect image when you only have a small data set can severely impact your model's performance. So we put a lot of checks and balances into our product to make sure that we're catching these errors and cleaning up our data set. And this was actually a major piece of the project that we worked on with Onder. A big piece of it was cleaning up the data sets to make sure that we got high model performance. I also want to point out that these projects tend to be very iterative. You don't just go straight line across like we kind of show in this diagram. We have those arrows on the top that also show that we're bouncing back to previous steps. So you might train your model, find out it's not performing exactly how you want to. You go back, label data, maybe add more data. You deploy your model, you might find out that you want to add a new defect class or a new technology that you want to inspect. So you tend to go back to these previous steps quite often. So having an end-to-end workflow that's really tightly integrated is super important. So you can kind of bounce back and forth very quickly to get the results that you're looking for. And I think it's also worth noting that deployment is not always the end of the project. Once you deploy a model, you're often maintaining it for a long time. So if you have new changes to your product or changes to the material that are being inspected, you want to be able to have a quick and easy way to integrate that new information into the models that are doing inspections. So again, that ties back to this end-to-end concept. And with all that in mind, I kind of wanted to take a second just to talk about how all that applies to the project that we're talking about today, the Automatic Defect Classification. So with this project, Onder and his team uploaded their existing image data to Landing Lens. So you're seeing the data browser on the right-hand side here. They were able to quickly review and clean up the classification to create a really robust data set. Able to quickly train multiple model iterations, deploy a number of those models and evaluate them in production in kind of a shadow mode where we weren't necessarily impacting production decisions. And once they were fully deployed, we now have mechanisms in place to continue to maintain those models into the future. And all of that was done with kind of this single platform, which is Landing Lens. So hopefully that gives an understanding of like how the product works. And now I wanted to turn it back over to Onder for the key results. And just to note, we have 6 minutes left. So
so I think you pointed out most of the critical things where we have to have we have to have a better training set in defining what is the defect codes. And that definition and the training set is the most important thing that, to start with, to start that iteration of model improvements. And the other main important thing, important item that we have actually instituted is to actually get what you can with by using the automatic defect classification, and this is and leave the rest to the operators. What we have approached in here is that we actually only accepted for implementation on the classifications that ADC can accurately or precisely and purely classify, and the ones that are not, that are confusing and that has a lot to do with the training set data, which has a lower volume. If you have a higher volume, you have a better chance of getting a better purity. And if it is a 80% and up in precision and or the purity, we consider that class as an accepted class. And by approaching this way, we actually were able to classify automatically more than 80% of the images with higher than 80% purity. Hence, the rest of the 20% of the volume of the data has been left to the operators to classify. So your workload has been decreased or improved by 80% by leaving only 20% to be classified. This selective class acceptance was actually the key, one of the key actually points of the success of the implementation in our manufacturing flow. On top of the better training set you have to start with. Next, please. And in approaching there, we actually apply the thresholding methodology, where we actually get a defect confidence for each classification that we have. Anything higher than that threshold that we applied, we accepted the defect code that has been presented by the ADC system, and anything less than that was left unclassified. So by doing the iteration, by improving the training sets and the types of images that the ADC is having the difficulty, we actually were able to minimize the lower threshold and upper threshold, so that we have minimal unclassified defect data, and hence we can actually fully embrace the ADC system in our systems. This is just to show how many iterations that we had to go through to reach to that 80%, and purity was our metric. And for a given defect class, as you see, we can start with 40%, but with model iterations can take up to 80% to be accepted in our scheme. And this is applicable for all the defect codes that we have. If we cannot achieve this purity, we left the defect not to be classified by the ADC and presented to the operators to be classified. Next, please. And the key results, I think this is kind of the summary of all the work that we have done. Previously, the automatic defect classification was being done 25% of the time by using other systems, but with the Landing AI implementation, we were able to get up to 80%. And this is actually 3 times better classification of the defects. And of course, this has improved our cycle time for each lot that 50% or more. And of course, this actually allowed us to train our human classifiers on the things that we really need to look at for classification. And obviously, as we are doing using an automated system, the consistency and quality of the classification came in with the system, and any misjudgment of the reject rates are minimized this way. Next, please. Yep. And with that, I can actually talk about this. So we are actually trying to, deploy this same methodology to other sites that are using outgoing inspections, and we are actually trying to utilize the same approach on other types of classification that we do in our fabs, and with that, I think our time has been completed. So